All right. So my personal interest in this was just I wanted to study the bird heads to see how they performed in the wind tunnel and kind of understand more about how nature performs in the situations that we as engineers want to look at with like aircraft and such.
So my co-op's in the space industry. That's not really an environment where there are many fluids present, but part of what we do. I mean, I'm working on satellites personally, but a lot of also what we do is we're looking at developments in rocketry and related technologies. And my interest in this is trying to see where we can get a connection between the design of the bird heads and how they operate, and applying that to spacecraft technology in terms of like reentry or space planes, and trying to improve the survivability and reliability of those vehicles.
Then my personal interest stems from my co-op at GM. I've been able to do airflow testing in there before. That's more testing kind of the airflow through like turbochargers and induction systems. So my interest is more along the lines of this is definitely something I won't see at my co-op. I'll see a lot of definitely automotive parts and stuff if I do airflow testing at my co-op, but I definitely won't be able to study lift and drag on a bird head there.
So the goal of our project is, of course, studying lift and drag on bird heads. So we wanted to kind of visualize that relationship for each of the bird heads, varying the angle between 0 and 45. We wanted to look at each of these bird heads and kind of understand a bit of their geometries and their shape, because nothing that we make as engineers or anyone in the industry makes something that's shaped like a bird head. So we really wanted to see how they perform. And then additionally, we wanted to learn more about how wind tunnels worked and how to use them, and increase our understanding of fluid mechanics overall by studying a biological application. So what are plunge diving birds? Just let's get that out of the way. Very simply, they are birds that dive into the water to catch prey, and this is usually in the form of fish, but also could be found in certain types of plant life. The gift that you see right there is just a common kingfisher. We did not study that one, but it was a very good demonstration of what it is. A common bird that most people are aware of that's plunge diving is a penguin. Those guys are really good at swimming, though. Our birds are not good at swimming. They have like no web feet. They have no adaptations to really swim in the water. Instead, they have to start in the air, really high up in the air, and then dive into the water to get enough distance in there to catch the fish. So one of the birds, just the other way, most of these birds are found in Michigan. We tried really hard to find only Michigan birds for this because we're all from Michigan. We really care about Michigan. We want to make sure that we find Michigan birds. So this is one of them. This is the belted kingfisher, found all throughout Michigan year-round. 28 to 35 centimeters, so it's yay big, and we are only studying the head, so that's pretty small. So we had to scale it up, and the ratio that we use was about 1 to 2. These birds dive at about a max speed of 11.1, and that is referring to the moment right before impact of water. That's what we wanted to look at for all these birds, their moment right before hitting water. Next bird is the common tern. This one migrates to Michigan in the summer, so it doesn't stay up here all the time, but it does come here for a good chunk of the year. It's roughly the same size as the kingfisher at 31 to 35 centimeters, and so once again, we had to scale it up by 2. These ones are our fastest birds, going at 22.2 meters per second, which is like twice the speed, so significant. Good. Then finally, we have the northern gannet. These guys could be found in Michigan. They could be maybe found in the Great Lakes, but usually they're found around the eastern United States, predominantly the coast, and they kind of migrate all along there. They are much bigger, so 87 to 100 centimeters. We did not have to scale these birds up, and while they are bigger, they are much slower divers. This clearly illustrates it as they don't start as high up as all the other birds, or they just don't reach as much speed as the other birds. So they only really do a 2.78 meters per second before hitting the water, and this is kind of showing what they do. As you can see, they start in the air, go into the water, and they will course correct a lot using their wings and such, which is something we did not account for. We're just assuming bird going as fast as possible.
So in order to do testing on them, we first need to make models of the bird heads, which not exactly something you can just find a CAD file online. So one of the things we did was we found a research paper from the Utah State University that had done kind of a similar thing, just focusing on like dynamics in water bird heads. So they had a lot of pictures of bird heads. So we were able to use Blender and basically outline the shape of the bird head and kind of form a model off that from like side view, top view, basically get a full 360 of what does the bird head look like, and then basically take that and then scale it up to the size we need. And then also in these, though, you can kind of see we added in some tubes, and then that's kind of where our pressure temps would go in order to collect our data during testing. Then the second part, obviously, is then we had to somehow mount these bird heads into the wind tunnel. So we just had a quick mounting bracket to mount on just the bar, and then this basically just uses the slot so we can easily just reach in, loosen a screw to be able to adjust the angle of the bird head while it's in the tunnel, as well as then using the same bracket for the bird head, so it's easy enough to just take one bird head out, put the next one in, connect the tubes for testing without having to do a lot of deconstructing and bolting the bracket back on every time. And then kind of you can see a little bit in there. We have we went for 6 different angles. So we put little markers on the bracket so we can determine kind of what angle we're at while we're testing, and we have a set system kind of to increase our angles. And then for making these models, we chose 3D printing because it was a quick, easy source over in the makerspace, especially with these large models, and relatively not an easy model to make by hand or something, as well as still keeping the bird heads light to not increase a lot of the weight they experienced during the wind tunnel testing. And then for the wind tunnel testing, we then mounted these to the bracket and connected up the tubes to the machinery, and then basically we determined the wind velocity based off type of bird, and then with gather data, we could loosen the screws and then kind of tilt the head up as we needed to. So for example, here's our turn at 0 degrees, and then over the course of testing got up to 45 degrees.
Little thing I want to add is what this would visually look like. The 0 degrees would be the bird essentially diving straight down into the water, while 45 degrees, we would increase angle, would slowly increase the angle like this until eventually we hit 45. So because we scaled the birds, we had to do some calculations what the new velocities would be. Because they got bigger, we know our velocities will get smaller, and to do that, we had to look at the Reynolds number and make sure that they were equal. So this is just showing that kind of work. One thing about the birds that's very big to point out is they don't have a diameter, they're not circular, they're not like a pipe, so we had to use a different equation for calculating the diameter using the non-circular geometry, and then plug that in. And then what you can see here in simplified scaling, so Reynolds number 1 equals 2, so small bird versus big bird. Doing the work here, key thing to point out is kinematic viscosity is still air, right, so they cancel out. If we looked at water, then those would still be in play and they would have had a factor in it, but we didn't get to look at that, sadly. And then our final equation is just our final velocity equals our initial velocity over the ratio of the small bird over the big bird.
Excellent.
So additionally, the end goal of this is to calculate lift and drag, or the coefficient of lift and drag. So these are what these equations look like. Through our testing, we found the force of drag and the force of lift. Density is air, velocity is the thing we just proved earlier. Area is the funny one. This is the one that gets interesting, that required a bit more work to put into, because there is no standard bird size. There's no CAD for this out there already that we've mentioned or looked for. So we had to figure out a way of doing that, which required some approximating. This is what we did for scaling. Essentially what we do is for 2 birds, because the gannet wasn't scaled, so we didn't have to do anything there, we used a different method. The kingfisher, we looked at it and said, okay, it looks fairly square-like, or like rectangular shape, so we just called it a rectangle, which is not the most accurate thing, but it worked. And then for the tern, we noticed it had a very rounded head, so we kind of said it had a rectangular base and a circular head, and that's what we worked with there. And then those equations you can see for area and perimeter, which are important for later. Josh wants go back. If Josh wants to explain how we found area initially.
Yeah, so if you go back, those images there are at 0 degrees. Getting the measurements for the other angles was interesting. And Blender's a really good program. That's just something it can't do. So what we did was we set the camera. Well, first we tilted the model up to the angle we needed. We set the camera a known distance away, and basically just took a picture. Using that, I took that picture into another software, cut the image out, and it would tell me the number of pixels. And then we knew the width of the bird in millimeters, and we also knew it in pixels.
Right.
So I used that, got a conversion between millimeters and pixels, then used that to get area.
Excellent.
Thank you.
Outstanding.
Thank you.
Very innovative thought, using technology, figuring out the problem and making it work, figuring it out. That's what engineering is all about. Outstanding thought.
Thank you.
Sorry. Go ahead. Just had to say that. Go ahead.
So then here's the first of our data. This is for the Kingfisher. You can see up there our initial area and our final area at 0 and 45 degrees.
Yes.
Our velocity there from the wind tunnel, it was 4.92 meters per second, which roughly corresponded between 16.7 and 17.3 hertz. Those hertz increased by angle. And then you can see there on the side the lift and drag coefficients. The data's kind of interesting. We weren't fully sure how to interpret it, so we assumed a sort of parabolic relationship, which sort of fit. It really depends on what coefficient we're looking for and what bird. It sort of worked. You can see we have R squared values here. A little bit smaller for the lift, 0.73, which is not great, not terrible, but for the drag, that's a R squared value of 0.94, almost 0.95, which is a lot better. Then this is for the, there we go. There's for the turn. Again, there's the areas there at 0 and 45 degrees. Velocity almost double at 8.05 meters per second, which again was fan hertz between 17.8 and 18.2. The relationships here for the drag and lift coefficients were sort of different. We did still assume a parabolic relationship just to keep them all the same across the birds. And you can see there, sort of similar. The R squared value is going to have sort of a lower one for the lift. This one is a 0.57, so almost 0.5 or 0.6, and then for the drag coefficient, an R squared value of 0.92, a little bit worse than for the Kingfisher, but still workable. Then for the Gannet, this was an interesting one, which we'll get. Yeah, we'll get to why later. Again, there's our areas. Velocity a lot lower, 2.68, which is lower than both the Tern and the Kingfisher, which we think corresponded to why our data is the way that it is. The fan hertz also very low. It's kind of hard to get it to stick to that. So, which something we'll talk about later. So that probably contributed to the lift and drag coefficients there. Again, still a parabolic relationship, and you can see with the R squared values, it's kind of a mixed bag. I mean, for the lift coefficient, we have a R squared value of 0.4, which by far is our lowest.
Question.
Sure.
Did you hold the density constant in all the tests, or did you calculate the density each time?
I believe we kept density constant.
Oh, okay.
So yeah.
Okay. No, that's fine. That's good. Wanted to just trying to identify the variables which could possibly contribute to the source of error. That's all.
So yeah, like I said, the R squared value there for the Gannet lift coefficient is 0.4, which is by far our lowest. However, our drag coefficient R squared value is 0.97, which is our highest.
Yes.
So again, a mixed bag there. So this is the bird comparison. This is essentially just a combination of those past three graphs stitched together essentially, and you can kind of hear this shows you the intricacies between the three different birds, and they all dive, but how they do it kind of this can kind of show you that, and kind of see some interesting things here, like for the lift coefficient, you can see it kind of changes. So if you're going for, if you're looking at a Tern, 27 degrees, it has by far the most lift, or the highest lift coefficient, but for 45, it's by far the lowest. And then for the drag coefficient there, you can kind of see how the different birds pick up drag as they change angle. So you have the Tern there, relatively low, Gannet here very high, and then the Kingfisher sort of middle throat.
And the one thing I'd like to add to this is that we are looking at living creatures who have evolved over a long period of time. They are not engineered for certain applications. So with this data, the only thing I would say is, one, we only got one data point for each measurement, sadly. And two, these bird heads are so uniquely shaped that trying to predict how they would accurately behave is going to be very difficult until we get more data on this, and there isn't really data for us to compare to. A lot of other studies looked at different factors of these birds. Okay.
Yeah.
So kind of speaking of that, potential errors and stuff that we discovered along the way.
Angle bird head. Okay.
Yeah, so one of the potential issues is just during the course of testing, there's of course just human error on how accurate are we on the specific angle we're targeting.
Right.
Because it's a difference about 9 degrees between each one. And when when you're trying to, we have a mark on there, but that could still be off by a few degrees depending on how close we're
Sure.
getting the mark.
Yes.
Especially, ideally this would have been basically a separate hole to each bolt size.
Right.
So that way we kind of know it's a set angle. Fortunately, with it being such a
Right.
small span, trying to fit six holes over there, it basically ends up being a slot anyways.
Sure.
As well as then just kind of any human error, maybe in like consistency of reading measurement equipment, it happens too.
Yeah, so we mentioned a bit earlier with Josh that the Gannett speeds are really low, and the wind tunnel had a very tough time keeping a consistent value. It kept like changing very small amounts at that low speed, and we had issues with that because we can't really say with extreme confidence we got the exact value with how much it would kept shaking a ton. Like all the other birds, fairly good. We could get it at stable value, but with the Gannett, we had to kind of take our losses and just hope we were
Sure.
darn close.
Sure. Okay.
But we made sure we had the same value on the equipment reading, but who knows how accurate it was because things were changing so much. That kind of goes into low resolution measuring equipment. Our values, on the presentation we showed like 4.92 meters per second is the value that we went with the wind tunnel. Our calculated values are actually a bit different from that, but that was the closest value that the wind tunnel could show us.
Right.
The range on the wind tunnel might be very large, but the resolution between each data point, it's like a difference of 0.09. So like it has spacing between each point. So it only updates after a significant change, not as it like continuously changes, which kind of was an issue with us because our values were significantly smaller and we couldn't get that fine data. And then
Yeah, for area and model approximation, this, in the beginning at least, sort of ties into human error. I mean, can't exactly go out and catch a kingfisher and get the measurements for it, so we had to go, again, first of all, secondhand off the Utah paper to make the Plunge model. So already there, it's a little bit of approximation. Then one thing we noticed pretty late into our calculations were actually that the pictures we grabbed were for slightly wrong angles, and we didn't have enough time to go back and take the pictures and do the method I mentioned before. So we knew 0 and 45 were correct.
Right.
So we figured out the equation for area versus angle. Then we used that to get the values that we use for our actual calculations. Looking back, the equation we got and actually going in and doing the pixel, like taking the pictures and doing that, those are accurate up to I think like 5 decimal places.
Okay.
So different method than mentioned before, but both are still valid.
Yes, yes.
So some project feedback and recommendations. First of all, we wanted to look at the water side of things,
Yes.
and we calculated what the velocities would be for using the wind tunnel and for water
Yeah.
based on that equation earlier. It would have been like 0.02. So really small, smaller than what the wind tunnel could do.
Yes. Yes.
Which is very unfortunate because we wanted to see if some of these birds were better suited for water because we know that terns go deep into water because of their high speeds, and some of these, and like the Gannett doesn't as much. And so it would have been really cool to see how like water and and drag and lift on in the water side of things would have played out. But we don't have a water tunnel. Very unfortunate, but it's what it is.
Another thing was just kind of trying to schedule time. We had, I don't know,
It was tough this semester.
yeah, over 10 teams, I think, scheduling projects. So it's kind of a thing of like, if our testing takes a little bit longer, it affects the next group, kind of just snowballs up in timing, as well as just other classes trying to use it and stuff as well. So just scheduling time is kind of just the biggest issue too, just trying to get testing. And if you realize that, oh, we wish we could get like redo this measurement or something, it comes into a little bit of, we don't quite have time to redo it.
Right.
Yeah, and then just having more time for the project. This is kind of going into scheduling time for the wind tunnel. I mean, I really like this project. All the ones did pretty good, but at the end of the day, work for the project didn't start until 6th week,
Yeah.
so we didn't really have a lot of time. And I think if going forward, students were told about the project, first, second week, we might have more time to.
Okay, but the students, they chose their own project, and so, we didn't have the flow lab experiment until week number 4, because that was when we talked about the Bernoulli equation and speeds, and so how could we have started the project earlier when you didn't even know, when you didn't have a topic
So
yet?
what I would say is the awareness of the project was much earlier.
Okay.
And then introducing like the idea of it, maybe showing some examples much earlier and saying, this is what you can do.
You're right.
We'll have you pick the topic
topic,
later, but
Yeah.
so you're at least aware that it's a possibility.
Yeah.
And then some people can start thinking of some things they might want to look
Yeah,
at.
even if we don't know the specifics,
Yeah.
at least giving us some time to come up with some topics, and then even if we have to change it later, at least we have a heads up.
You know, I mean, honestly, we didn't even decide to do it until fourth week. You know, just because of the class size. Because
Sure.
It's, you know, as you can see, it's a lot of coordination,
Yeah.
a lot of work. But do you think, though, that the project should, this project should be just a requirement of the course? Because then, if it's a requirement of course, then yeah, you can talk about it first week, second week, and say, hey, it's coming, and inform your teams. But do you think, though, because it's optional, and you pick your own project, you decide if you're going to do it or not, that gives you a stronger motivation, more interest in your chosen topic, because it's optional. You don't want to do it, you take the final exam.
Yeah, and what I would say is that there's definitely a trade-off to it,
Yeah.
taking the exam, doing the final project. Me personally, this is one of the few classes out of my entire academic career, I'm a senior at this point, this is one of the few classes that actually had me do a project at all like this.
Yep.
It's not that common throughout a lot of the classes earlier on. And this year I have 3 projects, but that was by sheer coincidence,
Okay.
and this
Yeah.
is one of them.
Okay.
Yeah,
So-
I mean, I know the curriculum is changing, so I mean, going forward, students may have more projects, but
Yeah.
my first academic term here was fall of 2021, and in an engineering class, this is probably one of the first projects I've had.
Yeah, I would agree that the new curriculum will probably involve more projects, because now thermal fluids and heat transfer will at least include 3 or 4 laboratories a term.
Yeah.
Okay, and that may facilitate more projects, because students now are exposed to different laboratory equipment,
Mhm.
and maybe it'd be easier to structure a project.
Yeah.
So, okay. Good. All right.
Last slide.
Okay.
Yeah, just thank you.
Thank you.
And any questions?
One question.
I had a question. Just in the beginning, we were talking about the birds diving into the water. How are they able to do that without getting their wings
So,
in the water?
could we go back to that GIF? So there's a lot of things that they do to control for that. One of the papers that we studied talks about the mechanics inside the bird's head that makes it so they don't take any injury. The thing with their wings, though, is they tuck them in. They tuck them in there.
Right.
And then when they get really close to the water, they want to slow themselves rapidly, so they expand their wings out. And that's just kind of control their angle at the last possible moment for the bird. Additionally, the birds, they've had a lot of time to figure this out. So their bodies are at least designed well enough to not break upon hitting the water. Now, granted, it can still happen. There's certain angles of attack the birds want to approach and certain speeds they want to do, but they are relatively equipped to do this repeatedly because this is their hunting style.
And probably also that their skeletal structure is more able to absorb compressive forces than, say, a human's neck and spine. So they probably have more cartilage, and they're better able to absorb compression than maybe a human is.
So that is actually what the paper talks about, why human divers can't do this.
Yeah.
And one of the main factors for these birds, at least one of the birds, is that they have this fluid packet in their head that absorbs a ton of the force.
Yeah, and to see that, just basic logic, it would make sense that because over decades, they have developed something in their spines or in their heads to allow them to absorb shock and dive in the water. So you're right. So that's good.
Fun little thing, if you want to watch these birds dive, I recommend looking up a video of Arctic terns. There's some nice videos out there from the BBC and such, and they dive really deep. We looked at common terns because they're Michigan, but the Arctic terns, those guys are the real diving champs.
Yeah. I have to admit, when you guys first talked about this project, I said, they're crazy. But I didn't. I wanted to support your enthusiasm and said, well, let me see how far they can take this idea, okay? But you guys did a great job.
Thank you.
I'm pleased that you guys chose this project and did the research you did on it, and it was an excellent, outstanding effort. So and I think that this is why you have to let students just choose their own project, and try and support it, and to keep them enthused, to support their enthusiasm, and because this actually was a project out there, but clearly it involves fluid mechanics. So that was good.
Thank you.
All right, guys. Thank you.
Thank you.